This problem states that superheated water vapor flows through a pipe of diameter 20 centimeters at 1000 kPa, 400 degrees C, and 30 meters per second. And it asks to determine different rates of transports. So since it's superheated water vapor or steam, the best choice is PC model. And it's obviously a flow state since it gives you a velocity and it's flowing through a pipe. So we'll go to test calcs, flow states, PC model, test app or test calcs, and we'll start entering our data. Since it asks for a rate of transport of X or G, you'll want to do a dead state, which is state 0. So just enter your pressure and temperature, just two properties, just to get the baseline thermodynamic properties. So that was 1000 kPa and 400 degrees C. Calculate that. There you go. You'll notice that X or G, the psi 0 is 0. Alright, and now for state 1, we're told that pressure 1 equals P0 or 1000 kPa. Same thing for T1 equals T0 or 400 degrees C. And we're given velocity is 30 meters per second. It didn't say anything about height, so we always just assume Z is 0 whenever it doesn't say anything. And it gives us diameter, but there's no diameter option in here, so we're just going to have to do that for area down here. And we're just going to enter it as equals 3.14 times the radius, which is going to be 0.1 meters squared. Alright, and then we have all our values entered, so we hit calculate, and you get your m.1, which is about 3.07 kilograms per second, which is the answer to part A for the rate of transport of mass. Now the next part asks for rate of transport of kinetic energy, which there's two ways to solve that. You can either do Ke dot equals 1/2 mv squared or 0.5 times m.1 times velocity 1 squared, all divided by 1000 to get it into kilowatts. And you'll get about 1.38 kilowatts for the rate of transport of kinetic energy. The other way to solve for that is knowing that E is equal to U plus Ke plus P. I'm just typing this out so you can see it. If you entered this, it would show an error. But you know that PE is 0, so you can figure out that Ke is equal to E minus U. So the other way to solve for Ke dot, I'm just going to name it Ke dot 2, is equal to m.1 times E1 minus U1. Hit enter, and you'll notice that you get the exact same answer, so either way works. The next part asks for a rate of transport of stored energy, which is going to be capital E equals m.1 times E1, and then flow energy, which is J dot times m.1 times J1, and then flow rate of energy, which is going to be S dot m.1 times S1, and lastly it's going to be X or G, which is psi. Psi dot is going to be m.1 times psi 1. And there you go, you get all your answers all in kilowatts. The next part asks how the answers would change if the steam was treated as an ideal gas rather than the PC model. So we will hit super calculate from our PC model, and it'll generate some test code up here. And we can just hit Control A, Control C to copy it, and then go to flow states, and then the IG model for ideal gas. And then we can Control V that code in, and then hit load, and then hit super calculate, and you'll get all the answers for the IG model. We'll go to the state panel to see n dot, which is right here, 3.03. For the PC model, we got 3.07, so it's fairly close. And then back to the IO panel, we got all our answers for the others down here. So we got about 1.36 for KE dot, and I screenshotted the answers from before. We got 1.38 before, and so those answers are again fairly close. However, the flow rate of stored and flow energy are found to be much smaller than they are for the PC model. We have 1288 and 2230 versus we had 9,087 and 10,029. So they're a lot smaller. This is because the PC and IG model use different reference values for the internal energy. And entropy is also referenced differently in the different models. You can see that here we got 33, whereas with the PC model we got 22. So overall, the PC model is much more accurate for steam, because steam isn't an ideal gas. It is something that often goes through phase changes, so the PC model is a much better choice.